So the original method is actually called Stone's strongly implicit preconditioner. Okay, and they use the acronym SIP for it. Okay, by the time we finish today's discussion, you will probably have a fairly good idea of why it's called a Stone's strongly implicit preconditioner as opposed to a solver. Okay, we already discussed in the last class what a preconditioner does. A preconditioner is nothing but if I have a matrix A times phi equal to Q, a system of equations, it modifies the matrix A in such a way that the resulting system is easier to solve or gives faster convergence. Okay, it's better conditioned and therefore gives faster convergence. So that's actually what Stone tried to do. He took the matrix A and then he played all sorts of acrobatics with it and put it in a form that lets him solve it much faster. Okay. So here's the original reference. As you can see, it's a pretty general title. It says Iterative Solution of Implicit Approximations of Multidimensional Partial Differential Equations. Okay. It was published in the Siam Journal of Numerical Analysis in 1968. So what we are going to discuss today is the 2D version of what he did. Of course, this is applicable to 3D also, except that the math gets a little bit more complicated, but the same ideas hold. Okay, so we are going to look at the 2D version of what he did and pretty much focus on what we get out of, let's say, a Poisson equation. Okay, so we are trying to solve del square phi equal to S phi. All right, and once we do our finite difference, as we know, we get these 5 diagonals. Okay, so what Stone first did was he wrote this equation in this form. So he named the 5 diagonals as E, F, D, B, H. Okay, so E is, as you can see, this guy here is the diagonal. Okay, and then here is your top diagonal, which corresponds to that, and then the sub diagonal, which corresponds to that, and then we have 2 diagonals far away. One of them is that, and the other is that guy. Okay, we talked about this matrix structure in the last class already when we did finite difference in 2D. So that's what he did. He first wrote the whole thing in that form, 5 diagonals, and the right hand side he called it Q. Okay. Now, as I said, this can be done in 3D also. We are talking 2D here, and no matter what method you use, you are going to get this kind of a structure as long as you use a second order scheme. Whether it's finite difference, finite element, finite volume, it doesn't matter. Okay, as long as you are using a second order scheme, you are going to get these types of equations with 5 diagonals in 2D, and if the mesh is perfectly Cartesian. So in general, we can write this as A times phi equal to Q, as you know, and then here is the structure of the whole matrix. As you can see, I have labeled the 5 diagonals. The middle one is called E, and then the one on the top is called F, and the one top far away is H. D is the sub, and B is the one far away at the bottom. So here is your southern node, northern node, eastern node, western node, and then this is of course the diagonal right here in the middle. Those are the contributions of the various nodes. Okay, and then here is your solution vector right here. Remember, as you recall, we have numbered all the nodes sequentially so that we have one long unknown vector. Okay, and then the right hand side, we are just calling it Q through Q, Q capital K. Now the right hand side may have source terms, it may have additional terms that came out of boundary conditions, it could have anything. This is just a general representation of the algebraic equations. Alright? Any questions so far? Alright, so step 2, Stone first rewrote the original equation in its correction form. Okay, and we talked about the correction form in the last class. I will revisit it shortly, but before I do that, here's what he did. He first defined a residual, okay? And instead of using, for example, we were using phi star as the value of phi at the previous iteration and phi as the value of phi at the current iteration, he actually started using superscripts for the iteration number. So for example, r with a superscript n means this is the residual at the nth iteration, okay? If I write r with a superscript n plus 1, then it would be the residual at the next iteration, okay, and so on. So he started using these superscripts, and therefore the residual at the nth iteration is basically the entire equation, okay, q minus a times phi. You can write it as a times phi minus q also. He just wrote it as q minus a times phi. It doesn't really matter, okay? That's the whole equation. And then he also defined a change in the value of phi between iterations, which is phi at n plus 1 minus phi n, which is the phi prime we had defined when we derived the correction equation. Remember, when we did correction equation, we said phi is equal to phi star plus phi prime, okay? Phi prime being the correction. Instead, Stone called it delta, and that's the notation we are using, okay? So at any iteration n, we have a change between the next iteration and that current iteration, okay? That's how we defined it. So we have a residual and a change. So in terms of the residual and the change, we can write the correction form of the equation as the coefficient matrix A times delta is equal to R, okay? And one might ask, okay, how did you get this equation? Let me just refresh your memory. And go back to our, well, here, okay? So if we go back to our previous lecture, see, here is what we did. We started with the original finite difference equation. We plugged in a phi star plus a phi prime, and then we ended up with this equation, which is nothing but, if you think about it, this is A times phi, or sorry, phi prime is equal to R, okay? In Stone's notation, this would be A times delta is equal to R. Okay? So that's the correction form of the equation written in matrix form. Everybody with me? So that's the notation he's using, and so if we go back to what we have here, that's basically what we have done to convert the original equation to a correction form. Okay? Any questions so far? All right. So this is where his method really starts. So next he proposed that the matrix A is factorizable into a lower triangular times an upper triangular matrix, L times U. Okay? Now, the point is, this is a proposition. Just because you want to factorize something doesn't mean you can factorize something. Okay? I mean, we know this from our middle school algebra, that if I have x squared plus 2x plus 1, that can be factorized, but if I have something else, that may not be factorizable because the factors are basically not integers. Okay, so it's difficult to factorize it. So that's the idea, that just because I want to factorize it into L times U doesn't mean that it's doable. Okay, it's something that has to be possible. So at this point, this is just a proposition. Later on, we will examine if this is at all doable or not. Okay, but this is the idea he started with. He said, how about we factorize A into L times U? Okay. Now, why did he want to do that? There's a big reason why he wanted to do that, and it's a very good reason, okay, as you will see. Suppose we are able to factorize, then the A matrix we can write as L times U. Right here. Alright. If we are able to do that, then we can split up the solution into two stages. We can say, we can define another quantity, this part here, okay, we can call that Y. Alright, and we can first solve L times Y equal to R. At any iteration my residual is known because I've started with a guess, I compute my residual, so I know my residual vector. I know my L vector because L and U have been derived out of factorization of A, so I know my L matrix. If I know my L matrix, I can solve, and my R matrix, I can solve my Y. Okay? If I can solve for Y, then I can solve the second equation because I would know my U matrix and I know my Y matrix from the solution of this guy. I can determine my delta. So it's basically the solution has been broken up into two stages. First stage, I would solve L times Y equal to R, get my Y, plug that into the first equation, solve for U times delta equal to Y, get my delta. Once I get my delta, I have my change, I add it to my previous phi, and I move on to the next iteration. Okay. Now, why would that be better than just solving for A times delta equal to R? Well, if you think about it, and we talked about this, how does Gaussian elimination work? Gaussian elimination has a forward elimination step and a backward substitution step. And we said the forward elimination has number of unknowns cubed. That's how the number of operations scale as n cubed. Okay, whereas the backward substitution scales as n squared. Okay. If you think about it, since L and U are upper and lower triangular matrices, what we are really doing when we solve this is just a forward substitution. Because the matrix that you have in front of your unknown vector has already been triangularized. Okay, it's already an upper triangle or lower triangle matrix. So I can start from the first one and say, okay, this guy is equal to the right hand side, and then substitute it into the next equation, solve for the second one, and so on. So this is basically a forward substitution instead of a backward substitution. It has only n square operations. Okay? And then stage 2, you do the same. And you have a backward substitution. Okay? Because in this case, you're starting with an upper triangular matrix. So everything on the bottom half is 0. Everything in the top half is non-zero. And you start solving with that, you do a backward substitution, again n square operations. Okay, so the bottom line is, if I can factorize A into L times U, I can actually get a solution of the system of equations in one iteration, because this is a direct solution, right? We're not iterating or anything. I could possibly get it in one iteration with only 2 n square operations instead of n cubed operations. Okay, now think about that. If your n is even 1000, which is a pretty small number, you've reduced your number of operations by a factor of 1000 because you're multiplying n squared by 2 instead of n. Okay, huge saving. So we're getting exact answer for the same equation without any iteration, all right, with much fewer operations. All right. Now, it's important to remember that this is all still hypothesis at this point, because we still don't know if we can really factorize A into L times U. All right? But if it was possible, then it would give us huge savings and a solution strategy that would not require any iterations. It would be 100% implicit. Yeah.
So this delta that you solve for takes you immediately from
immediately to the final solution. That's it.
Okay.
Yeah, you just calculate your delta, add it, and that's it. You're done. Okay? Because there is no approximation in the math, as you can see. We haven't neglected any term or approximated any term, any of that. Any other questions? Okay, so that is the premise on which Stone built his method, because he sort of, you know, it's like looking backwards, and a lot of smart people do that. They think ahead, and then they say, okay, if I could do this somehow, then this thing would be a gem. Okay, that's how he started thinking. So I talked about this also, that just a few seconds ago, that instead of k cubed, you're getting k square operations. Okay, that's really the advantage of the method. So now let's revisit this issue of, is A actually factorizable into L times U? Okay. So here is what Stone proposed. So Stone said that I'm not only going to propose that this is factorizable into L times U, but in addition, I'm going to propose that L and U are both banded matrices. They are not even full upper and lower triangular matrices. They each have only 3 diagonals. Okay? So this is what he proposed. He said, okay, how about I make L a lower triangular matrix with just 3 bands, and U an upper triangular matrix with just 3 bands, not even full matrices. Okay? So if you, and these are the notations he used. His lower triangular matrix, he had 3 diagonals, which he called D, C, and B. And his upper triangular, the diagonal, he made it 1, because, you know, you don't need to make 2 different diagonals. You can just have 1. So he made that 1, and then the other 2 he called E and F. All right? Now, in terms of notations, I just want to caution you a little bit here. If you go back, the matrix elements here of the original matrix are all capital letters. Okay, so just keep that in mind. Don't confuse these capital letters with the small letters we are using later on. Okay, so these are all the coefficients of the original matrix, which he called capital B, D, E, F, and H. Okay, when we go to the L and U matrices, he denoted them by small letters. Okay, B, C, D, E, and F. All right. So our contention is that L times U should give us back A. Okay. Now let's see what happens if we work backwards and actually multiply L and U and see what we get. Okay. So if we multiply L and U, and you know, I'm not doing the math here, but it's pretty easy to do. You just do a row by column multiplication, take those kinds of structures and multiply them. You will find that the resulting matrix has 7 diagonals instead of 5. Okay. Now remember, your A had 5 diagonals. So right there you have a problem. How can a matrix with 5 diagonals be ever equivalent to a matrix which has 7 diagonals? Impossible. Okay. So right away he hit a roadblock with this hypothesis. Okay. So instead of 5 diagonals, you get 7 diagonals, and that implies that A is not exactly factorizable into L times U. Okay. But here is what Stone said. He was smart enough to realize that, hey, I don't have to really solve A times delta equal to R, because I'm really using this system of equations to predict a correction. And I don't have to be 100% accurate in my prediction. I can make an approximate prediction. The only caveat is, since I'm making an approximate prediction, I have to iterate. Okay? So remember, this is the holy grail of iterative methods. Your prediction of change can be anything. It doesn't matter how you get it or what you do. Okay? If this is my initial guess and this is my correct answer, how I go from here to here is really irrelevant. Okay? I can say, okay, I have a method which is going to zigzag like this and finally get here. That's fine. If it does it in 2 iterations, that's fine. Okay? There's nothing which says you can't do that. All right? So he realized that since I'm solving the correction equation, or I intend to solve the correction equation, yes, if I use an approximate form of A times delta equal to R, I will not get the solution in 1 iteration, but it should be fairly close. Okay? If my correction is good, or if my approximation of A is good. Okay. Remember last class we talked about what do preconditioners do? Preconditioners massage the equation A into a form that gives us faster convergence. That is precisely what he's trying to do. He's saying, okay, I have this A times delta equal to R, but I'm not going to solve that equation. I'm going to massage the equation to a form that lets me get to convergence faster. Okay? So he said, okay, how about I try to do an approximate factorization, which may have some errors, but if I do 2 or 3 iterations, that error will get corrected and I'll have the final answer. Okay? So if you, and this is what I said in the previous slide here, if you actually multiply these two guys, L and U, the matrix will look like that. 7 diagonals. Okay? So this is your L times U. That's what this is showing. Okay? And I have denoted them by E, D, F, G, H, and so on, but with bars on top of them. Okay? To show that these are not the coefficients of the original matrix. All right? So you can now what happens is if you compare this to, let me go back, okay, let's just, okay, so these are my L and U coefficients, okay, with the small letters. If I multiply them and write them in this form, the form that I show here, you can derive these relationships very easily, where you can say, okay, my capital B will be the small b, the capital C with the bar will be small b times E, and so on. So this is just multiplying row times column of L and U. Okay, that gives you those relationships. So in other words, whatever I have in this matrix with the capital letters with bars on top of them, they can be expressed in terms of the coefficients of the L and U matrix. Okay, it's a simple multiplication, that's all. Okay, you can try it for yourself, it's not very difficult. Any questions so far? Okay, now if I compare this to the A matrix, there are two quantities that are extra. One is this diagonal here, and the other is this diagonal here. They did not exist in the A matrix. The A matrix had those 3 diagonals clustered in the middle, and the H and the B far away. That's it. Okay, these 2 extra diagonals have shown up now. Okay, so if I take this matrix and then multiply it with my phi vector, okay, with phi 1, phi 2, blah 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 up to phi k, okay. So if you look at multiplication of that with that, okay, this is what you're going to get. You're going to get your original 5 diagonals. As you can see, this is my diagonal element. This is the k plus 1, k minus 1, k plus n, k minus n. But then because of the extra c and g that we had in the new matrix, we get these additional terms. Okay, the c actually ends up multiplying k minus n plus 1, and the g ends up multiplying phi k plus n minus 1. Okay, because if you look here, see, h is multiplying phi k plus n, right? This guy is multiplying phi k plus n, if you look at the vector that it's multiplying. So this guy must multiply the phi value just above it, which would be phi k plus n minus 1. Okay, so that's what this is showing. Similarly, if you go here, c is multiplying phi k minus n plus 1, because b is multiplying phi k minus n. Okay, c would be multiplying phi k minus n plus 1. Okay, which is this guy here. Everybody follow that? So we have these extra terms, extra two terms that show up. Okay. So now Stone said that, well, now I can't make this matrix equivalent to my A matrix. I can't really balance coefficients. It's like saying, okay, I have 7 terms equal to 5 terms. Okay, how am I going to balance this? So he said, somehow I have to get rid of that C and G term. In other words, the 2 red terms in that equation. I need to get rid of them and express them in terms of the other 5 terms somehow. Okay, if I can do that, then I'm back to 5 diagonals. And then I can make an equivalence between the A matrix and the product of the L and U. Okay? So if we think about it, what is really happening? So here is our stencil. Our stencil actually was just that part. This is what we had in our stencil. Okay? Now we have these 2 additional terms which have introduced really 2 additional nodes, their influence on the center node. That's what has happened. Okay? It's almost as if the value of phi at the kth node is now being influenced by not 4 neighbors, but 6 neighbors. Okay? That's basically the physical interpretation, or you can call it the geometric interpretation of that equation. So now Stone said, well, if that's the case, if these nodes are now influencing that node, okay, how can I get rid of those nodes? Okay. So he thought about how can I eliminate that northwest and southeast nodes, and he said, well, one of the ways to do it would be to use a Taylor series expansion. I can approximate the value of phi k minus n plus 1 in terms of perhaps phi k and phi k minus n and phi k plus 1. So he said, maybe I can approximate the value of this guy in terms of that guy, and that guy, my 3 closest neighbors. Okay, and similarly, I can approximate the value of this guy in terms of this guy, and this guy. Okay, that was his argument, that should be able to do that with Taylor series expansions. Okay. Any questions so far? Okay, so if you now think about it, I'm going to expand this guy about that guy. Okay, now this is, yeah.
He used Taylor series expansion on the 3 terms, that's the diagonal, the northwest, southeast.
This way you mean? Yeah, it eventually comes to the same thing. If you add the 2 Taylor series expansions, that's what you're going to get, essentially. Okay, so let's go through this, and you will see it's pretty much comes down to something like that. Okay. Okay, so if we just start from the northwest node, so we are going to somehow, we are trying to get rid of that term. Okay, so we do a Taylor series expansion of that guy about our central node. Okay, now if you think about it, this is a 2-dimensional Taylor series expansion, because this is negative x, negative delta x in that direction, and positive delta y in that direction. Okay, so it's a 2-dimensional Taylor series expansion. So if we just keep the first order terms, throw away the higher order terms, you get phi k plus n minus 1 is equal to, it's approximately equal to phi at k minus d phi dx times delta x, minus, because we are going backwards, that's backward in x, and then forward in y, so plus delta y times d phi dy. Okay, this is an approximation, of course, because all the higher order terms are gone. Okay. Then further, he said, the d phi dx at k, this guy, I can write it, again, this comes from a Taylor series expansion really, I can write it as phi k minus 1 divided by delta x. Okay. So the first derivative in x I can write as that minus that divided by delta x. Again, that comes from a one-dimensional Taylor series expansion from k minus 1 to k. Okay. Same thing for the y derivative. He said d phi dy. We can write as phi k plus 1, that guy, minus that guy divided by delta y. Yeah.
Is dy just one long, or is it n?
dy is the spacing between nodes.
Okay.
Yeah. So everybody get that? So basically 2 levels of Taylor series expansion he did. One to actually write out the corner value in terms of the central value, and then approximating the derivatives that show up using nodal values again. Again, I keep repeating that these are all approximations. If you actually derive the error terms will be all first order. Okay? Any questions so far? So if I now take that guy and that guy, these two guys, and plug it in here, okay, into those two spots, this is the final expression I get. So phi k plus n minus 1, this guy has been expressed in terms of these 3 nodes. And that's the expression. Okay? It's only accurate up to first order accuracy, but nevertheless it's an approximation. It's a valid approximation. Okay? And if you use the same procedure, you can do it for the southeast node. You're going to get an expression which looks like that. All right? So now we go back to our equation and we replace this guy and that guy by our approximations. Okay? Once we do that, here is what we end up getting. So now we have combined terms. We got rid of those 2 nodes and we've combined terms. So L times U becomes that. So I've plugged in those values. Okay? And if you rearrange, you end up with just 5 diagonals because we've gotten rid of those 2 extra terms. Okay? So we end up with just our old set of 5 terms, k plus n, k plus 1, k minus 1, k minus n. Okay? So this is the restructured LU. Important to note, though, is that this is an approximate form of A. This is not the exact A. Why? Because we have thrown away certain terms in the Taylor series expansion. Okay? Everybody understand that? So now we can make the equivalence between our original 5 diagonals, which were B, D, E, F, and H, and it's pretty obvious, you know, if you just compare this bottom equation here with the original equation, it's pretty obvious that these are the relationships you're going to get. Okay? Now, what Stone also did is, I forgot to mention that, you see this alpha floating around, okay? So what he really did was, he said, well, these are approximations that came out of the Taylor series expansion. They are not exact. Okay? So what I'm going to do is I'm going to pretend that I introduce another fudge factor alpha, which is a value close to 1, because 1 would give us exactly what I got out of the Taylor series expansion. Okay? Something other than 1, okay, would give us something different from what came out of the Taylor series expansion. But then he said, well, you know, I'm going to solve the correction from the equation. I'm modifying my A. Who is to say that I need to use the exact Taylor series expansions? I can use anything I want. Okay? I can just modify them by some fudge factor alpha. So he introduced this fudge factor, you can call it Stone's factor alpha, and then he plugged everything in, and that gave us this extra guy everywhere. Okay? So later on you will see that this alpha in the Stone solver is actually used to fine-tune the convergence. Okay? Depending on what value you use, it's problem dependent also. You can get slightly better or slightly worse convergence. Typical values of alpha are around between 0.9 to 1, so it's pretty close to 1. Okay, but sometimes people find that with 0.92 you get the best performance, something like that. So there is an optimum value of alpha. All right, so those are the equivalent relationships. Any questions so far? And once you have the equivalent relationships, from that you can combine that with the relationships of that we had between these barred diagonals and the small letters in the L and U to derive actually these guys, the small guys, in terms of our original diagonals. Okay. Remember what you have when you have the PDE that you've discretized. You have these 5 guys. That's all you have. Okay. From those 5 guys, what you need to do is derive these guys so that you can solve the L times Y is equal to R, and then the U times delta is equal to Y. Okay. So our objective really is to express the small guys, these small letter guys, in terms of our original diagonal. Completely get rid of the barred diagonals. That was just an intermediate step we took to keep the algebra relatively straightforward. Okay. So if you combine those two, here are the expressions you come up with. So you see, this is all the small letters expressed in terms of the big letters. The big letters are the coefficients of your original matrix. The small letters are the coefficients of your L and U, which is the approximate factorization. Okay. One thing to note here, though, that these relationships are recursive. For example, to calculate B, you need E. Okay. If you look at the expression for E, to calculate E, you need B. So where is the chicken and where is the egg? Okay. And it requires a little bit of thinking on how to proceed with this solution. And, that is why for this particular method, I'm actually going to give you a small code where this is all done. Okay. And you can just use that and see what is actually done. The thing is to understand that for any index value of 0 or less than 0 or negative, basically you have a value of 0. So that's really your starting point. Okay. So even though E requires or B requires E, as you can see, there are certain values of E that are known. The moment I go 0 or negative index, okay, that E value is a 0. It's known. So therefore I can calculate the B. Okay. So there's a little bit of trick here in terms of how to calculate these coefficients. It requires a little bit of thinking on how to program it. Okay, but it's doable. It's been done many times. So I'll show you a program or share with you a program to do that. So here's the overall algorithm. So we've now gone through the derivation of how this is all done, but let me just sort of draw the bigger picture now. Okay. So first thing is you derive your nodal equations, finite difference nodal equations, and fill in your matrices B, D, E, F, and H, which are your 5 diagonals. Okay. And this will include not only interior nodes, it will also include boundary nodes. So for boundary nodes, for example, if you have a Dirichlet boundary condition, your B, D, F, and H will be 0. You will only have E equal to 1, a 1 in the diagonal. Okay, those kinds of things. So for the entire set of nodes, including boundary nodes, you have to assemble your matrix and fill out B, D, E, F, and H. Okay, that is something you have to do. Otherwise, of course, you can't solve the problem. Okay, there is no getting around that. So that's the first task. Then you use the recursive relationships I showed in the previous page and calculate your small letter coefficients B, C, D, E, and F. These are the diagonals of your L and U. B, C, and D are diagonals of the L matrix. E and F are diagonals of the U matrix. Okay, so what you're trying to do is you're trying to construct the LNU matrices so that you can solve, okay, from the original diagonals. So that's the next step. Any questions so far? Now, as we said, the whole method, because of the approximation of the factorization, that the fact that L times U is an approximate factorization of A, you have to still iterate. Okay? So, because you have to iterate, just like every other method that we have talked about so far, you have to start with a guessed value of phi. Okay? And let's call that initial guess the 0th iteration. So we are calculating, we guess our value of phi and we calculate residual at all nodes, which is R superscript 0. Okay? Once we have our R superscript 0, we are going to solve for this vector y using L times y equal to R. Okay? When we start off, this will be R0. But for future indices, for future iterations, that of course will get updated. Okay? But that's what we solve for. Now this is the forward substitution step, requires only n square operations. Okay? So then we have the backward substitution step, where we take the result of this first solution, y, and that becomes our right hand side here, and now we solve for the change, delta. Okay? So forward substitution, backward substitution, you solve for your change, and then you update your phi, which says phi at the new iteration is phi at the old iteration plus the change. Okay? If you want, you can add an under relaxation factor there, but it's not necessary. Typically, you will not need to for a linear problem, because these are linear equations you're solving. Okay? And then you monitor your convergence and repeat steps 3 through 9. Okay? The residual we already talked about. We are already calculating that, so it's already there. All you have to do is square and add it. That's it. You don't have to have any additional steps to calculate it. Okay? So you square and add it, get your L2 norm, monitor your convergence, and then you repeat this part here. Do not repeat that part. That is fixed, because your coefficient matrix is fixed. Okay? Now, there may be problems where the coefficient matrix is also a function of the solution. Okay? Like when you solve the Navier-Stokes equation, the coefficient matrix is a function of the velocity field itself, because it's a nonlinear equation. Okay? In that case, yes, you have to do step 2 also. But in general, step 2 is frozen. Once you've determined your coefficients, they are there. Don't need to calculate them anymore. Okay. So yes, there are overheads in doing this step, but it's minuscule because you're doing it only once. You're not doing it every iteration. Okay. So if you now think about it, Gaussian elimination takes n cubed operations. So suppose you have a simple problem with 100 by 100 mesh, okay, which is 10,000 unknowns. All right. Now, instead of n cubed, which is 10,000 cubed floating point operations, you have reduced it to 2 times n square operations. Okay. So if you think about factoring out 10,000 square, instead of 10,000, you're using 2, right? That's the reduction in the number of operations. So as long as your Stone's method converges below 10,000 iterations, you will have gains over Gaussian elimination. Okay? And chances are, instead of 10,000, it will take 10 iterations. So you will eventually get a huge benefit out of using this, even though this is an iterative solver where you're doing 10 or 100 iterations. Okay? Or 10 or 100 matrix solves, actually. Because this solve is so much cheaper than the original Gaussian elimination solve. Okay. Any questions? So that's the method. Now here are some salient features of Stone's method. As I said, LNU is an approximate factorization because L times U is derived by using those truncated Taylor series expansions. Okay, and therefore you need iterations. Why does the method work? The method works because we are applying it to the correction form of the equations. Okay, you cannot apply this to the real equation. Why? Because then you are not solving A times phi equal to Q anymore. You would be solving some other equation. But you are always allowed to solve some modified correction form of the equation because it's simply predicting a correction. As long as that correction takes us towards convergence, it doesn't matter if I'm predicting a correction of 200 versus 2, as long as it takes me to the right answer. Okay, so that's the thing, that using the correction form lets us modify A, and modification of A, as I said in the last class, is really a preconditioning step, and that's why he called it strongly implicit preconditioner. Strongly implicit because we are really solving all the equations simultaneously in this case. We're not using Gaussian elimination, but that's the purpose we are achieving. As you saw, we are not talking about, okay, we keep this point in the this point in the stencil explicit, this one implicit. None of that showed up here. Okay, it's a fully implicit solution, really. This alpha, this fudge factor, as I said, this is used to alter the path to convergence. If that Taylor series expansion was 100% accurate, you wouldn't need any kind of fudge factor. You would just plug that in, and then out of that you would get basically the solution in one iteration. But unfortunately, we can't use the higher order terms in the Taylor series expansion. Okay. So that's why you have to iterate, and he used this factor alpha to tune the whole thing. Okay. So what